This video is in regards to a 2015 GMC Yukon Denali XL with the 6.2. So I don't actually have any film footage of me troubleshooting this vehicle, but I'm going to go over kind of what I did and what's going on with it. So this vehicle had a P0016. Actually, if you look at my history, I'm using the Ultra here. It's a Yukon XL 2015. There's the VIN. But P0016, crankshaft position not plausible. Right? Don't worry about these other codes. But that's the one we're chasing. So the history on this is, I believe the camshaft went out on this one. The lobes went out, lifter. So I believe the guy replaced the camshaft with an OE camshaft. Same type of camshaft in the lifters. And afterwards, this had a P0016 for this code. So let me show you the definition of the code in the wire schematics next and what I did. But before I do that, I do want to show you there is a service bulletin that can come in handy, and I'll show you here. The code he had is a P0016. This one right here. And we'll go to this. It's the same thing, it's just a PIP, but they added to it. They added the 2019 model. So we'll click on this one here. So he's got a GMC Yukon. He uses a 15.62. It's an L86 engine. So the condition, the P0016 is setting after internal engine repair. In other words, the engine base timing is not being set correctly. Now, this vehicle did have an internal engine repair. Like I said, it had a camshaft and lifters replaced. So when installing a chain and gear set on a Gen 5 V6 or V8 engine in the vehicle, it is difficult to get a straight on visual of the timing marks for alignment. Basically, they go through this, talk about counting your teeth and all this stuff. You can read through that right now if you want, but I'm not going to read through it all right now on camera here. But it says you can incorrectly install it. And the reason is because number 3, index 3, is the oil feed hole number 3 is not being centered in the block, throws the perception of the technicians off during alignment. So it looks like it's off, right? That's showing it's on, but it could be off. So it shows up here. Like I said, P0016 setting after internal engine repair, which it was. The engine base timing is not being set correctly, which I'm going to show you how we found that on the oscilloscope. But let me pull up the schematics next. All right, so P0016, crankshaft position, intake camshaft position, not plausible. Well, for an overview of the system, you can refer to this, the camshaft actuator system. So it has a camshaft actuator system, which advances or retards the timing. There's a solenoid on the front of the camshaft that pushes a plunger out. There's 12 volts going to the solenoid. The computer controls it, pulse width modulated. It lets oil go through it to advance or retard the timing. But when it's at idle, it'll be 0 degrees. It won't. The spring is stationary. The oil pressure would have to take over, depending on what port it goes through, to advance or retard the timing. But the ECM compares the signals of the crankshaft position sensor. It says both camshaft position sensors. This is a generic code, but it's one camshaft position sensor, and it says it's out of sync. Well, how? For the set the code, the deviation of the relative camshaft position is greater than -11 degrees in one direction or greater than +11 degrees in the other direction, measured in degrees of the crankshaft. So 11 degrees, 11 or more, that would be your mode 6 data, basically. That's your tolerance when it's thrown in the code, which we're going to a little bit more later. And you can go through all this stuff, but I take it with a grain of salt. So now, let me go how this kind of thing, how this works, and I'll show you why we believe the base timing is off. So, the actuator system, I'm not going to go into this too much. You can read it, but it has this 2 different passages for oil flow, a passenger cam advance and a passenger for cam retard. That's pulse width modulated. Right, that's how it's doing that. So now let me go to the schematics next. Before I go there, also, it has a lock actuator. When it's not advancing and returning the timing, the spring holds it there. and then the oil pressure, like I said, will advance or retard the timing. All right, so I pulled the schematic. So before I even scope this with the oscilloscope, I hooked the scan tool up. I got that code. It will not let me clear the code. It will not let me do a cam crank relearn because there's an actual fault. It's checking for this code continuously, and it keeps setting it. That's why you cannot do any of this. But if you look at the schematics for this L80, for this engine, the 6.2, you got your Hall effect sensors, right? So you have 3 wires on each one. You got your crankshaft position and your camshaft position. 5 volts feed them. You go to ground. And what I did is I probed on connector X3, pin 26, because that's the feedback to the computer, and X3 pin 33. 26 for the crank, 33 for the cam. 2 channels. Kind of a pain to get at on the computer, but yeah, they remove a bunch of tape and, you know, back probe it and all that stuff. So take the back shell off the connector. So we probed there on the with the oscilloscope, and I'll show you what we did next. But before I get into that next with the oscilloscope, the crankshaft reluctor ring, which is on the back of the crank, it says there are 58 teeth or visible magnetic segments on the edge of the crankshaft position reluctor ring mounted on the crankshaft. Each tooth or magnetic segment of the ring is spaced at a 60 segment spacing with 2 missing segments for a reference gap. So 58 plus 2 is 60 per service data. And that'll come important here for the next couple steps. All right, I'm trying to find a good picture. So this is the crankshaft. So basically there is, if you count these teeth, there's 58 teeth, but remember it said it's 2, there's an open spot, so 59, 60. So this is a 60 times crankshaft position sensor. 58 teeth, and then there'd be 2 that would go in there, right? But they use that one so they know where to start. The Hall effect sensor picks that up. Now I want to show you the valve timing. So if you look, this might not be the best picture, but imagine 1, 2, 3, 4. 2 big ones, 2 small ones. That'll come important. This is where your camshaft sensor is picking up. This is your cam gear. And then if you look at, let me see here. This is your you know, variable valve time assembly. There's a plunger that goes in here, advances or retards the timing. This is spring loaded and it stays there, spring pressure, and the oil pressure got to overcome, advance or retard this. Well, if you look, this guy here is the plunger that goes in there. Depends how far this goes in or out. We'll let it advance or retard from oil pressure. And what controls that, it's hard to tell, is this guy. It's 12 volts going in. Computer controls the ground pulse with modulated. There's a little plunger on the bottom of this. That right there, that little plunger right there, pushes that in and out. There's your 2 pins. All right, so now this scope work right here is from a 2010 6.2. Now I know we're working on a 2015, but if you look up the part number for a 2010 and 2015 for this cam sprocket variable valve timing, it's the same exact part number. It's the same thing. It's the same amount of teeth and stuff, which we'll go over later. Cam gear, same amount of teeth. Crank gear, same amount of teeth. So this blue tracer, this is a known good at idle. This blue tracer is your crank sensor. This red is your cam sensor. So the crank sensor, if you count all these, starting with this big one all the way through to the end, you're going to have 60, or no, 58, I mean, because there's an open spot. From here all the way over, you're going to have 58 of these. I'm not going to count them on camera, but I did count them. So there's 1, 10, 20, 30, 40, 50, and 58. Right? And that's what we've seen on that encoder wheel on the back of the crank, because this is your crank. And there's actually, it's a 60 times because, you know, that spot that would have 2 in there. And then your camshaft has 2 big spots, 2 small spots. Again, that is on Sorry, it's hard to film and pull up these pictures. Too big, too small. Two bigs, two smalls. So now, God, I got bad glare again. Hang on. So now what we're going to do is we're going to pull up our oscilloscope. This is from the car now. I saved it. I saved two different ones. Yes, I don't care about demo mode. So we're going to open the file, open the waveform. This is that idle from the vehicle. I'm going to open. I saved it from the 2015, right? So let's just go right in there. So 58, 58, 58, two bigs, two smalls, two bigs, two smalls. So let me zoom in to get some. Don't worry about this hash, that's just noise. I'm going to put a low pass filter in there. But what I want to look at is compare this supposedly vehicle that has a tooth off compared to a known good. Oh, and by the way, if you take, these are each worth, okay, 360 degrees in a circle. This is the crankshaft. Well, 360 divided by 60 is 6. Right? 360 divided by 60 is 6. So each one of these is 6 degrees. Because 6, imagine these are 6 degrees each. That's what they're worth. 6 times 60, 6 degrees times, there's 60 of these, because you'd have to take up that one spot, like I said, which would be, I guess I already got rid of it. No, I didn't. There's 58, 59, 60, right? So then you take your calculator. I need somebody to film while I do this. Oh, come on. 6 times 60. 60 of these times 6 degrees, you're going to get 360 degrees. So each one of these is worth 6 degrees, which will come in part to our next step. So let's compare this now. So this is a known good one. So just look from here to here, which is going to be the center of the two big ones, and it's off of the cam, or off the crank. So the center of the two big ones, we want to compare count from here to here, and here to here. So let's count these first. All right, so let me try to explain this here. So two big humps opposed to that one. Two big humps opposed to that one. So if you count, I'm not going to count the big one, I'm going to count 1, 2, 3, 4, 5, 6, 7, just before it's flush. This is a good one, so I have 7, right? If you count up here, 1, oh, come on, focus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically 2 more to get over to this. So it has 2 more of the 6 degree ones than it has on the good one. Well, 2 times 6 obviously is going to be 12 degrees roughly off, or a little bit more than 12 degrees off, right? 12, you know, if it was 3, it'd be 3 times 6, which would be 18 degrees. That's kind of hard to tell because I don't have cursors on this one here. So 12 to 18 degrees off. But, you know, 12. Well, if you remember from the tech data, it said if it's more than 11 degrees, then it would throw this code. And that's exactly where we're at, above 11. And that's why it's throwing the code. And you can check that anywhere else on the graph. Like, let's go to another spot. Let's zoom out. And then normally what I would do, which is nice, is you can put your cursors in here. You know, 2 crankshaft revolution, 720 degrees. You can put those where you want it. You can measure from T1 to T2. You know, I'd put them in here and put my cursors and do the math. But the one I got from a guy on the web, it doesn't have the cursors in here. So the only thing I can do, that'd be a little more accurate, obviously. But this is still pretty accurate, what we're doing. But the cursor thing would be perfect to do, you know, 2 crankshaft revolutions from here to here and do the same thing up there and see where we're at. But this works as well. It's always nice to have good waveform, have a good waveform library. So let's do this one. So the first small one is going to be, we got, oh my God, focus, 1, 2, roughly 1, 2. That's the first small one. Which up here, the first small one is this one. Well, if you look, 1, 2, 3, 4. 1, 2, 3, 4. So you have 4 instead of 2. So there's 2. There's your 2 again. Your 2 times 6. So here's your 12 degrees off again, which is above your 11 degrees. And if you do the math, the cam gear has 44 teeth. The crank has 22 teeth, and you can actually physically count them. If you take, you know, each tooth is worth 8.2 degrees, or 8.1 and some change. 8.2 times, you know, 44 is roughly 360. Same thing for the crank. Do the math, 16.4 degrees, roughly, or 16.3 and some change times 22 is your 360. You can do the math and figure out it's a tooth off, right? And that proves it with this oscilloscope readings. And we just checked it in a couple different spots. All right, so another more in-depth thing. This is the mode 6 data for this exact vehicle, for this exact year. So component, crankshaft position, camshaft position, correlation, bank 1 sensor A, P0016. Monitor description. This is right from GM. Detects cam to crank misalignment by monitoring if cam sensor pulse for bank 1 sensor A occurs during an incorrect crank position. Malfunction criteria: 2 cam sensor pulses more than -11 degree crank degrees or before -11 degrees or before +11 degree crank degrees after nominal position and 1 cam revolution. And it tells you how it's checking for and all that stuff. And like I said, this scope reading here shows that this is a known good one, and this is a bad one. A known good one and a bad one. We are always roughly two of these off compared to the known good one. Well, if they're each worth 6 degrees, that's 12 degrees, which is above the 11 degrees. And if you do the math, it's about a tooth off. Between, not ignition timing, but between cam and crank timing, which goes back to that TSB I showed earlier. So I guess what you could say, well, where do you get how you know it's about a tooth off? You know, and we're seeing 2 of these is 6, you know, 2 times 6, 12 degrees. Don't worry about this one. It's roughly, it's kind of hard to tell because this thing's printed out. Like I said, I wish I had the cursors. I do on here. I don't have it on this one. But we're saying it's 12 degrees. Well, if you take, we already did this math, 16.4 plus 8.2, that's what each tooth is worth for both of those. Take that and you take them and you divide it by the 2. There's your 12 degrees roughly, because that's an average. It's a cam crank correlation, not ignition timing, but cam crank correlation. Like I said, not to beat a dead horse, but I believe the base timing is off on this engine because this known good one, I know it's from a 2010, but it's the same part numbers, same stuff at idle, VVT, 0 degrees. When it's running, it's not advancing a retardant because the engine computer's not telling it to. And we have, you know, 7 here. And we have 2 more, you know, up here, 9, right? So everything is off by 2 of these, right? Like I said, this is your crank, this is your cam. 58, but it's actually a 60X because of those, it has to have those 2 spots. And then you get your too big and your too small for your cam. So what this thing needs to be done, it needs to be taken apart and recheck that base timing. So I imagine that brings up the question, was there any misfires on this vehicle? No, there's not. according to the scan tool data I have, reading it, there's no misfires, and it actually runs pretty good. But this code will not clear. Now, if according to our data, it shows it's a tooth off because, a known good compared to a suspected bad. Well, if you were to take a Chevy 350, for example, there's 36 teeth on the cam, and then half that 18 on the crank, and you do the math, 10 degrees times 36 is 360, 20 degrees times 18 is, 360, do the math. Of course, it's going to be off more. So one tooth off on a 350 compared to a, 5.7 off a tooth compared to a 6.2 is going to be completely different, because these teeth, or imagine these as being coarse teeth, and these are fine teeth. It's a lot more accurate. If you're one tooth off on this, you're going to be more, you can do the math, same thing, and you'd be off more degrees than we are with this one, because it's a finer tooth, right? It's more accurate. So, which I know I keep being a dead horse, but again, if you're, we have a count in here that needs to be 7 according to a known good waveform. We can validate with another waveform, but this is what we have to validate right now, that it's 7, and then this one it's off by 2 more, right? So that is the issue, and that equates to roughly 12 degrees, depending on where you're measuring from. Like I said, if I can get another data that actually had cursors on this stuff, then I can measure it on here, and then we could get exactly what we're off. But I believe it's the timing, the base timing, that needs to be validated. Cam phaser, I looked at that. I don't think it can be put on wrong. There's 3 bolts. One's got they're not, I don't know if they're staggered evenly, or they're staggered one different, or there's a bigger hole. I don't think it can be put on wrong. And it was never taken apart. So we do have a good square wave, 5-volt square wave. So I believe it needs to be taken apart and checked, the base timing according to that TSB. And then, yeah, see what happens. So that'll be it for this video.